Hi, so tonight we're going to derive the Michaelis-Menten equation. This is important because it describes the kinetics of enzymes when they're substrates. So we're going to look at this top left corner right here, and we're going to see if this variable E is enzyme plus variable S, which is substrate, yields in a forward reaction to make the enzyme substrate complex. This reaction can also go in the reverse direction, which we'll explain a little later. Then you have reaction 2, which is the enzyme substrate complex in a forward reaction to make enzyme plus product. So the next important thing to do is to associate variables to the forward and reverse reactions that I just mentioned. So the forward reaction in equation 1 would be K1. The reverse reaction in equation 1 would be K-1. And the forward reaction in equation 2 would be K2. So now if we add these two equations together, we're going to cancel out E here and here, and ES, and we'll just get S yields P, or substrate yields product, which makes sense if you think about it logically. So the next thing we need to take in consideration is the ES. So the ES complex equals the sum of reactions that decrease its concentration. And that's important to sit down and break it piece by piece to see what will actually increase the concentration versus decrease the concentration. So if we look right here at this line, we have the instantaneous rate of change for the enzyme substrate complex, and then we're going to look at this segment right here. And the reason that there's no minus sign in front of it is because when you have enzyme and substrate together, you're going to yield the enzyme substrate complex, which is going to increase the concentration. So that is why it is written that way. So then you have a subtraction sign right here because when you take ES and K-1, you're going to decrease the concentration of the enzyme substrate complex. So that is why it is written like that. And the same thing goes for this section. So when you take ES here and you go with K2, you're going to decrease the concentration because you're breaking it up into enzyme and product. So, and then that would equal 0. So the next thing we need to realize is that it's very hard to figure out the value of unbound enzyme, or just plain concentration of E. So in order to do this, we need to find the concentration of E total. In order to do that, we're going to take concentration of E total right here equals the concentration of E, which is what we want, plus the concentration of the ES, or the enzyme substrate complex. So in order to isolate this variable, this one right here, we're going to subtract ES, concentration of ES, I should say, from both sides, and you'll get the concentration of E equals the concentration of E total minus the concentration of the enzyme substrate complex. So now we're going to take this concentration of E, and we're going to substitute it back into right here. So then we're going to have this stays the same, equals K1, equals, instead of having the concentration of E, we're going to have the concentration of E total minus the concentration of ES times the concentration of S, minus, then the rest is the same, which you see here, all equaling 0. So the next step would be to distribute both K1 and S into this portion of the equation. So we're going to take K1, put it to these two terms, and put S into these two. Same thing. So we're going to have it K1, concentration of E total times the concentration of S minus the minus K1 times the concentration of ES times the concentration of S minus everything else stays the same from there. So now the next thing that we're going to do is to move all the terms with ES onto one side of the equation. So the only one that doesn't have it would be the one right here. So then everything else will get moved to the other side, just like that. So that is all written right here. Yes, all written right here. And then from that, we're going to take out the ES from the one side that all has ES's in all the terms. So once we do that, we're going to have K1 times the concentration of S plus K-1 plus K2. Because if you look right here, we're going to pull out the ES, pull out the ES, and pull out the ES. So that would be what's left. And then this side remains the same because it never had a concentration of ES to begin with. So now the next step would be to divide to get the concentration of ES by itself. So we would divide by this on both sides. So that is why you get the concentration of ES right here. And then you get K1 times the concentration of E total times S over K1 times S, concentration of S I should say, plus K-1 plus K2. So the next step would be to multiply by well, I'm sorry, the numerator and the denominator by 1 over K1 and 1 over K1. So in order to do that, you would get this right here. So you would get concentration of ES equals concentration of E total times concentration of S over the concentration of S over, I'm sorry, it's not over, plus K negative 1 plus K2 over K1. So then now we need to think about something that relates everything together. So we need to realize, if you look up here, that D, concentration of P over dt, equals the instantaneous rate of change for product P. So that's important because that equals the function of the reactants. So now if we look at reactants for K2, right here, K2 would be ES. So now the instantaneous rate of change for product would equal K2 times ES. So the next step in getting the desired equation would be to put in the concentration ES and put it into right here where it says concentration of ES. So now it's important to realize that the instantaneous rate of change of product is also equal to velocity. And then that is also equal to K cat times the concentration of E total times the concentration of S over the concentration of S plus Km. So we're going to break that down a little bit further, but the first thing we need to establish is the fact that we have K cat. And K cat equals the turnover number. And the turnover number is how many molecules enzyme can utilize per second. And that's important because K cat is also equivalent to K2. They're the same term. So now it's important to realize that if you have K cat and you're going to multiply it by the concentration of E total, you're going to get the concentration, Vmax. And the reason you're going to get Vmax is because K cat is the turnover number, so it's how many molecules an enzyme can utilize per second. And then if you have the total enzyme concentration total and you multiply those two together, that will ultimately give you the maximum velocity of the reaction. So now we need to realize why from here, substituting that into the equation that we did over here, this turned into Km. And that's simply because Km is the Michaelis constant, which equals exactly what this is. So it's easy to go from one to the other here. So overall, this is the desired equation that we were looking for, that we derived all the way from here, all the way down, and got to this point. But there's two more concepts that I kind of want to touch upon really quick. So when we talked about the Michaelis constant, we said that that equals K negative 1 plus K2 over K1. But also I want to say that Km is also equal to the concentration S. And when it's equal to concentration S, you have, if you would plug in instead of having Km here, you have S, you would have Vmax times the concentration of S over concentration of S plus concentration of S. And when you would do that, you would have, basically you would have Vmax times the concentration of S over concentration to concentration of S, because then you're adding them together. And once you would take out the concentration of S, you would see that Vmax divided by 2 would be Km. So Km equals the concentration of S at which the reaction rate is half of the max velocity. So then another important piece that I want to bring in to account with Km, regarding Km I should say, Km also tells the affinity of an enzyme to a substrate. So if you have a low Km in a certain reaction, you're going to have high affinity. So it would be more likely that substrate will go to enzyme and the reactions would occur. But if you have a high Km, you'd have a low affinity, and then the opposite would happen. Not a lot of enzyme and substrate would react, and not a lot of product would be formed. So overall, that's the Michaelis. I'm drawing a blank because that took about 9 minutes. The Michaelis-Menten equation, and that is how you would get it, and those would be important terms and concepts behind it. Thank you.